In the previous lecture, we discussed the normal to the plane and normal plane. One is normal plane and second is normal line. So it was a line perpendicular to the tangent at point P. This is called a normal line. Now, this is a normal line. If we discuss normal line in a osculating plane, that is called a principal normals. So what is principal normal? Principal normal is a normal, which is a normal line, the normal in the osculating plane. So this is on the osculating plane at a point P on a curve is called a principal normal. So that is a difference between normal line and principal normal. Principal normal basically is a particular case of a normal line normal direction in osculating plane. So that is called a principal normal. Now third definition, which is a binormal. This is a normal perpendicular to principal normal, which is called a binormal. Clear? So this is a normal perpendicular to principal normal. So principal normal is perpendicular to tangent and binormal is perpendicular to principal normal. So all the three are mutually orthogonal, mutually perpendicular. If they are mutually perpendicular, then T vector, this is a T vector, which is a unit vector along a tangent line, and this n vector, which is again unit vector, this is along normal direction, right? And b vector, which is again a unit vector along binormal. So all the t and b, they form a right-handed system of axes. Clear? So first is t, second is n, and third is b. So b can be written as t cross n vector. For example, if we take in the form of circle, so here it is a vector t, here it is a vector n, and here it is a vector b, right? So the positive direction is t cross n equal to b, n cross b equal to t, and b cross t equal to n. Clear? So in this way, we can find the uh, value of third vector from two vector. So similarly, b vector can be written as this b vector can be written as t cross n vector. So they form a right-handed system of axes. They form a right-handed system of axes. Now these three vectors, they are very important for differential geometry. Even the entire differential geometry is on the basis of T and B. T and B means unit tangent, unit normal, and unit binormals. Clear? They form the three plane, osculating plane, second is normal plane, and third is rectifying plane. So remember all these things that we will use in the entire chapters of differential geometry. So now, this T vector, if we take our room, suppose we are sitting in a room, if we are sitting in a room and in that room, suppose this is a room, clear? So we are sitting in the room and we are sitting at this place. Suppose we are sitting at this place. This is some, suppose this is a some member A, clear? Now, the one direction of the room, this is a t vector. Suppose this vector is a t vector. That is, if you are your left hand side, if your left hand side direction is a t vector, and opposite to the face, this is n vector. Suppose this is n vector, and that is this direction is, this is a b vector. Clear? So this is a b vector. If this vector is a tangent, this vector is normal, and this vector is binormal. Clear? So this vector is tangent unit. So remember, in a when you are sitting in a room, your left hand side is a tangent vector, and your front is normal vector. This is a normal vector, and your left hand side is tangent vector, and this direction, which is perpendicular to the base, this direction is a binormal vectors. Clear? So first remember, when you are sitting in the room, then these are the direction. So visualize the direction T, N and B. So T is your left hand side, and N is in front of you, and binormal is that is perpendicular to the these base. Clear? So this is the direction that that is T, N and B. They are orthogonal system. Now, what is the plane? We know that, as we know that, osculating plane. So, what is osculating plane? Osculating plane, which contains which contains t and n vector. So, this vector is a yellow, this yellow part, which is a osculating plane. So, remember this yellow part where you are sitting. Clear? So floor of the room. Clear? So this is a osculating plane. Clear? So remember, this is T, this is N, and this is a osculating plane. And this plane, which is perpendicular to this tangent and normal, this is called a normal plane. This is a normal plane. Clear? So this is called a normal plane. So normal plane is perpendicular to unit tangent. So this plane is called a normal plane. Clear? So that is, we write in the red part. So this red part. So this red part is a, that red part is a normal plane. Clear? So this is a red part is a normal plane. Now after that, if it is a normal plane, after that, this part, your left hand side, this is a rectifying plane. So this is a rectifying plane. Clear? So this is a rectifying plane. Now in this form, if we take in this form, this base is osculating plane, and this base is osculating plane. Clear? And this is your front face is a normal plane, and your left hand side is a rectifying plane. So remember these three planes. So you are sitting on a base. If you are sitting on a base, you are sitting on a osculating plane, and your left hand side is a unit tangent vector, and front is a normal plane, and this is your left hand plane is that is a rectifying plane. Yeah. Now just to discuss these three planes. Now this osculating plane, which contains a principal normal vector and which contains a normal tangent, unit tangent vector. Remember this. Yeah. So what is the definition of osculating plane? This plane, any vector in this plane perpendicular to binormal vector. So remember this. So in osculating plane, which condition is satisfied? Which is this plane is perpendicular to binormal vector, right? Now what is normal plane? So normal plane is perpendicular to tangent vector. So this is a tangent vector, and it containing normal line, principal normal line, and binormal line. And this rectifying plane which is perpendicular to principal normal vector. So which contains a line, binormal line, and this is a unit tangent vector. So from these, we can visualize the plane and the vector T and B, and also the equation of all the three planes. Clear? Now from only this geometry, we can find the equation of osculating plane, which is a, if vector is capital R minus small r. So what is the equation of osculating plane? Capital R minus small r vector perpendicular to binormal. So their dot product is equal to 0. Similarly, in case of normal plane, similarly in case of a rectifying plane. Yeah. So just visualize the entire geometry, and then we can find the osculating and plane. Now, what is the osculating plane? So I repeat again, this is perpendicular to binormal vector. So their dot product is equal to 0. So this is equation of osculating plane. Now what is the equation of normal plane? So this is a normal plane and it is perpendicular to tangent vector. If it is perpendicular to tangent vector, so this is a equation of normal plane, right? So what is the equation of rectifying plane? Now this rectifying plane which containing two vector binormal line, and this is unit tangent. So it is perpendicular to normal line, principal normal. So it means the equation of rectifying plane is this is r minus small r dot n vector equal to 0, right? So this is the equation of rectifying plane. Now, what is equation of principal normal? As we find the equation of a tangent, then in that case it was r vector equal to small r vector plus lambda into t vector. Now here this t vector is replaced by n vector. So the equation of principal normal, which is equal to capital R, which is equal to small r plus lambda n vector. Similarly, in case of y normal, capital R, which is equal to capital R small r vector, and again this term, this t is replaced by binormal vector. Clear? These are scalar, lambda mu are scalar. So these are the equation of principal normal, binormal, and we already know the tangent. Now these definitions are very important. All these definitions. Now t is vector. Now differentiate this vector with respect to s is again a vector, right? So this is again a vector. Then its magnitude is a scalar quantity. So that is denoted by kappa, and kappa is called a curvature of the curve. So what is curvature? Curvature is magnitude of dt by ds. So which is a t dash vector. So this is a t vector dash. If t vector dash, so what is t? T is a dr by ds. So this will become a r double dash. So curvature is magnitude of dt by ds. Clear? So remember, it is not a dt by ds. It is a magnitude. It is a magnitude of dt by ds. Similarly, in case of torsion, so torsion, which is equal to rate of change of binormal with respect to s. So it is again in term of magnitude. This is denoted by tau. So what is tau? Tau is absolute value of dB by ds. So which is equal to b dash, magnitude of b dash. Clear? So this is called torsion, and this is called curvature, and its reciprocal is called radius of curvature. Its reciprocal is called radius of torsion. and radius of curvature is denoted by rho. This is denoted by radius of curvature, which is denoted by rho, so which is equal to 1 by kappa, and it is in case of torsion, this is sigma. So that is a make difference between these two. So rho is a radius, r for rho, r for radius of curvature. So first, so this is a sigma. Sigma is a radius of torsion. Clear? So this is a, so here we discuss in term of T and in term of S. Now in term of N, which is called a screw curvature. In term of N, so what is N? This is a, what is screw curvature? Screw or twisted curvature, which is dn by ds vector and its a magnitude. So this is a definition of screw curvature, and this can be written in this form, which is kappa square plus tau square and square root of all the term. Clear? So it is a, if it is a by using Pythagoras theorem, if this is a kappa term, if this is a kappa term and this is a tau term, so this is a tau term, so this is a squaring of this plus squaring of this and square root. So this is a screw curvature. If this length is curvature, this length is torsion, so this is called a screw curvature. So remember this, and this is denoted by dn, ds, and its absolute value, its magnitude, its length, and it is a scalar quantity. So curvature, torsion, and screw curvature are scalar quantities. So remember this. These are not vector quantities, these are scalar quantities. Now this is Seerecht Freenet formula. So this is very important result, and entire differential geometry on the basis of this result. So what is the result? This is a dt by ds which is equal to kappa n. Now it is a vector quantity. dt by ds which is equal to kappa n, dv by ds which is equal to minus tau n, right? So dn by ds which is a tau b, this is tau denoted tau b minus kappa t. So remember, first see this formula, then this formula. From these formula, we can visualize this formula, tau b minus kappa t. Clear? So here negative will be positive and positive will be negative. Tau b minus kappa t. Clear? So first t is with the kappa and b is with the tau. That is already we know that kappa is with the t, tau is with b, right? So dt by ds which is equal to kappa n vector, db by ds which is equal to minus tau n vector, and what is third part which is dn by ds which is equal to tau b minus kappa t. What is kappa and tau? These are the curvature and torsion of the space curve at point P. Clear? So this is very important result. Now, what is the proof of this result? We know that T is a tangent vector. Clear? So its magnitude is 1. Clear? Now, from this, its square of magnitude, which is again 1. So this can be written in this form. This is T dot product T, which is equal to 1. This values. If this is equal to 1, now differentiate with respect to S. Now first take its a derivative. So that is dt by ds dot t vector, right? Then plus t vector dot vector. This is dot dt by ds which is equal to 0. So it becomes t dot dt by ds which is equal to 0. Okay? So what is this? It is a t dash. T dash is perpendicular to t vector. So this is perpendicular to t vector. So that is written in equation number 2. Clear? Now after that, now we know that this condition, if scalar triple product is 0 then these three vector A, B, C, it lies in one plane. These are coplanars. This coplanar means which lies in one plane. Now already we discussed the equation of osculating plane. So what is the equation of osculating plane? So this is capital R minus small r, comma t and t dash. So the scalar triple product of these three vectors is 0. Then it means all of these vectors lies in this plane. Which plane? Osculating plane. So t dash, this vector, it means this and this lies in osculating plane. So it means t vector dash lies in osculating plane. Clear? So it lies in osculating plane. Clear? Now imagine the osculating plane as we discussed earlier. You are sitting in a room, your left hand side is t vector and your front is n vector and the third side is binormal vector, and where you are sitting, you are sitting on a osculating plane. If you are sitting on a osculating plane and t vector lies in that plane, so this t vector is perpendicular to b vector. Clear? So visualize that, then you will find this t vector, t dash vector is b vector. Now again you can see that if we go to the figure, so this is a, if it is the osculating plane, now this vector t dash lie in this plane. So what is this plane? This plane is perpendicular to this line. So what is this line? This is a binormal. Clear? So it means t dash vector, t dash vector, which is again perpendicular to, lies in osculating plane. So it is a perpendicular to b vector. Right? Now t dash perpendicular to t vector, t dash perpendicular to b vector, then it is parallel to its cross product. Right? So this is b cross t. So what is b cross t? It is n. So it means this t dash vector is parallel to n vector. So by definition of parallel vector, this can be written in this form. This is t dash lambda n cap vector, n vector. Now to find the value of lambda, so we take its magnitude. So this magnitude, what is its magnitude? That is kappa dt by ds. What is its magnitude? That is absolute value of lambda. What is its magnitude? Which is 1. So absolute value of lambda is equal to plus minus lambda. So kappa, this kappa, which is equal to plus minus lambda. So we take a positive sign. We take positive sign. Then lambda is equal to kappa. If lambda is equal to kappa, then this is the first equation. So dt by ds, which is equal to kappa n. So this is a kappa n. So this is our first result. Clear? Now second result, dv by ds, which is minus tau. So again we take on same parallel line, b vector dot b vector equal to 1. Now again differentiate, we get this b dot b dash equal to 0. So this is b dash vector perpendicular to b vector. Again we know that this b vector is perpendicular to t as well as n. So this b vector is perpendicular to t, right? Now b is perpendicular to t, clear? Now differentiate this with respect to s. So first its derivative is b dash dot t plus b dot t dash, right? Now by result number a, substitute its value, which is kappa n. Clear? If it is kappa n and these both are perpendicular, so its dot product is equal to 0. If its dot product is equal to 0, so we get this term. From this, b dash vector is perpendicular to t. Clear? Now b dash vector perpendicular to t and similarly B dash vector perpendicular to B, then this B dash vector is perpendicular to B cross at T, which is again equal to n vector. So it means B dash can be written which is equal to mu n vectors. Again, to find the mu, we are taking its magnitude. So we get this tau which is equal to plus minus mu. Now here we choose a negative sign. In the first case we choose positive sign. Here we choose a negative sign. Then dB by ds which is equal to minus tau into n vector. So that is our part B. After this, third, which is dn by ds. To find the dn by ds, we take the value of n vector, which is equal to b cross t vector. Clear? Because it is, this is, if circle, this is a t vector, this is a n vector, and this is a b vector, right? So what is n vector? N vector will be b into t vectors, right? Now differentiate with respect to x. So this is dn by ds. So first, don't change its position, because in cross product commutative property is not applicable. So b cross its derivative dt by ds, then its derivative dv by ds cross t vector. Now substitute its value. So which is kappa n, which is minus tau n. So this is tau, this is it, this term is tau n cross t. So if we are replaced by negative sign, then this will become t cross n. So this is a tau t cross n minus kappa, which is n cross b, these values. So what is t cross n, which is vector b? What is n cross b, which is vector t, right? So dn by ds, which is equal to tau b minus kappa t. So this is the third result, dn by ds, which is equal to tau b and kappa t. So these are the Serret, Seret, and Freenet formulas. Clear? So after that, that result also we written in the second form. Clear? If this vector d vector, this d vector, this vector which is tau t plus kappa b, this vector is called Darboux vector. Darboux vector at some point in a given space. Then show that result number 1, result number 2, result number 3, and result number 4. And remember it. Clear? So we will prove left hand side which is equal to right hand side. So I take right hand side because it is easy to prove this right hand side. Now what is right hand side? This is d cross t. Now substitute the value of d, which is tau t plus kappa b cross t. Now taking cross product, this will become t cross t. This is t cross t. This will become b cross t. This is b cross t. Right? So this will be 0 because cross product of same vector is 0. And b cross t, this will be n vector. So this will be kappa n vector. And kappa n vector we know that by Freenet formula. So which is dt by ds. So we get first result. Okay. So it is easy to prove by using right hand side, not by left hand side. Similarly, in the second case, we take d cross n, substitute the value of d, taking cross product, this cross product, and this will be v vector, and this will be t vector. So what is its value? Tau b minus kappa t. So this is a dn by ds. So it is our second result. Similarly, in case of third t cross b, now taking cross product with b. So this we take cross product again. So this will be 0 because same vector, and this will be t cross b. Now it is a negative because b cross t is positive, b cross t is positive, and t cross b is negative. So this will be become minus tau n vector. So it implies this dB by ds because this term is equal to this values by Freenet formula. Clear? Now the fourth result, which is a n cross d cross n, substitute the value of d. So this is tau t plus kappa b cross n. So this will become first taking cross product with t, then with b, right? So this is t cross n plus b cross n. So t cross n, which is a b vector, and b cross n, which is a t vector. So this is a negative t vector. So this will become minus kappa t. This is a positive tau b minus kappa t. Clear? So this is again taking with cross product with n vector. So this is tau n cross b minus kappa n cross t. So its value is t vector and its value is b vector. So which is equal to t vector. So that is our fourth result. So this is very easy to prove. Just start from the right hand side, okay, and use the previous result. So don't start from this side, start from right hand side, and you will get the this result. And in this result we are using the Freenet formula. Clear? Now after that, the necessary and sufficient condition that a given curve to be a plane curve if tau is 0 and given curve is straight line if kappa is 0. Clear? So if tau is 0, then the given curve is plane curve. If kappa is 0, then the given curve is a straight line. Clear? Now that we will discuss in the next lecture. So remember this result. If tau is 0, then it means the curve is a plane curve. If kappa is 0, then the curve is a straight line. Right? So this is the theorem that we will discuss in the next lectures. So